Cool. Yeah, so I'll be giving the PyTorch presentation. I'm Kiefer Akoba. I'm the Director of Operations for ScottyLabs. I'm glad all of you could make it to today's talk. So we're going to teach you how to use PyTorch and how literally anyone can make a neural network pretty easily. So just as a disclaimer before I get into the meat of the presentation, if you are an absolute beginner in machine learning, which is like maybe you know the basic concept of a neural network from like pictures you've seen in news articles, but you haven't really like delved into what they really are, what the different layers are, like activation functions and how you can manipulate them, you might want to try out Keras, which is a different, not different, but it is another Python interface. It works on top of TensorFlow, but it was made to be extremely easy to use and is very good for rapid prototyping a neural network that you want to create. You can see here, if you look at the code here, it is extremely clean. All you have to do is you say you're creating a sequential model. You start with some input, and then for each layer, you just say, my next layer is a convolution, my next layer is a max pooling, and so on. It's very simple and intuitive to use. That being said, it's not very flexible because of how simple it is to use and how much it kind of wraps everything together. But as I said, if you're an absolute beginner, this is still a great interface to use. And it still does quite a bit of stuff for most purposes. But with that being said, we can get into PyTorch. PyTorch does assume a little bit of knowledge in machine learning concepts, but I'm going to help give a little bit of a primer if you're a little bit confused in some of the concepts. And feel free to stop me if you have any questions. So what is PyTorch exactly? It is a machine learning library. It was developed by Facebook. It is, as I said before, it's extremely flexible. It really lets you delve into the parameters of a machine learning model and kind of change things around for your purposes based on your data. And it was originally created with the purpose of being able to utilize a GPU, which is what's located on many machines for fast computing of matrices. And it was really used to make use of those GPUs to make machine learning models run and train very fast. It uses something called tensor computing. We won't be going over that. We're just going to be focused on how to actually use the library to create the machine learning models that we want to make for any type of data we want. Specifically, we're going to go over ANNs and CNNs, and I'll go over those in a bit. So let's go over a bit of what exactly is a neural network, a little bit of a primer. Here are some basic ones. We have here on the left, some input layer. We have a hidden layer that does some computation on our input, and then it outputs it to our output layer. Some of you may have seen images like this. These are the images that like you see on a bunch of news articles when they're trying to like show neural networks. Here on the right, we have a slightly more complicated one. We have more hidden layers is the only difference. And with more hidden layers, you're allowed to do more computation on the input and be able to learn more about our data. Some more involved, complicated neural networks. We have here a convolutional neural network. We'll also be going over this in today's lecture. Not lecture, today's presentation. And I'll be going over more information about what it means, but we have another neural network here called a recurrent neural network. We won't be going over this one, but this one is good for time-based data if you want to look more into that. And there are a bunch of other type of neural networks, which we won't be going over, but if you're interested, these are restricted Boltzmann machines, autoencoders, generative adversarial networks, or GANs for short. All of these are what are known as generative models. And while we won't be going over them, you might want to look into them because they're pretty cool. They are what make things like, say, these images of human faces are not real. They were all generated by machine learning models such as these. So we won't be going over them, but if you're interested, you can definitely look into them more. Any questions about that so far? I can keep moving on. I can't see the chat, by the way, so Anushka and everyone else at ScottyLabs can let me know if anyone has a question. So generally, basically what you saw here is that every neural network usually consists of some kind of input. Some middle section here does some black magic. It could be anything based on our architecture. And then we feed all of, and then after doing some computation in the input, we feed it to our output. The output could be like a classification. Say we're feeding digits into our machine learning model. It would classify like whether if you gave it the number 4, it would say what its best guess of what the digit is. Hopefully it would be 4. Maybe the output is, like I showed before, it's like a generated face. And while I didn't put it here, it's very important that your neural network has some kind of loss function at the very end after getting your output. This is very important because this is what allows your network to learn from the data. So as an example here, let's say we built our neural network and we wanted to classify some digit here, some handwritten digit, it's 7. So what we do is what we call feed forwarding the input through the network, and then we receive an output. Here, the network thinks that the number is 1. Obviously, that's not right. So we would feed this into our loss function, the guess, which is 7, and the guess, which is 1, and the actual label, which is 7. We feed that into our loss function. The loss function tells you like how badly did the network do. And what we do is called back propagating the error. And we kind of just feed the loss backwards through the network. And while I don't really have that good of a visual to show it here, this is essentially what makes the network train and learn. Like, okay, I did bad on this input based on our loss function. So how should I change my parameters to account for this? So neural network training is all about doing this process of feed forwarding an input, feeding it into our loss function, seeing how badly it did, and then you back propagate those errors back to the neural network, and it's able to learn and train from that. And you just repeat that back and forth. So we'll be going over 2 types, the artificial neural network, ANN, and the convolutional neural network, the CNN. So let's go over that first one. The ANN is just a fancy term for literally what I was just showing before. It's the canonical neural network. It consists of an input layer, an output layer, and several hidden layers. Can you guys see my mouse? Okay, cool. I see Anushka nodding her head. So yeah, it's just an input layer of some size. Let's say in the earlier example, we had the handwritten digit. That is the number of pixels in that image is 28 by 28. So 28 times 28, that's 784 pixels. So our input would be size 784. Then we have some number of hidden layers. They can be any number, any size. And then our output would be, depending on our problem, I'll use the digit images as an example again. If we're trying to classify images, there are 10 digits that we would want to classify. So we would have 10 outputs of class 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The most important thing about a neural network here is let's zoom in on one of these nodes. Let's say we're zooming on this node. Every node has what we call an activation function. And this is the most important thing about a neural network. It allows us to learn like any feature of the data. If you're mathematically minded, you might want to look into what's called the universal approximation theorem. What it says as because of activation functions, it's what gives neural networks their power and why they're so popular in learning stuff about data. So let's zoom back. Some examples are ReLU, sigmoid, tanh functions. So let's zoom back out. So like I said before, you can have any number of hidden layers of any size. So I'm going to go over a PyTorch example. Let's say I'm going to use the digits example again. Let's say we have a set of some handwritten digits, and they are stored in images that are size 28 by 28. This is actually a very classic data set called the MNIST data set. It was what the first neural networks were trained on, and it showed just how powerful neural networks are at being able to learn stuff about data. So we're actually going to, I'll actually show how you can create your own neural network to train on this kind of data. And we're going to create an artificial neural network. We're going to be using this architecture. So pretty simple artificial neural network. Our input layer, like I said, it has to be 784 because the images are size 28 by 28. That's 784 total size. We're going to have 2 hidden layers. The first hidden layer will be size 128. It'll use a ReLU activation function. Our second hidden layer will be size 64, also using ReLU activation function. And our output layer will be, since there are 10 digits, we want an output of 10. We use what's called a softmax activation function. The softmax activation function is very commonly used for classification, like what digit is this, or is this a dog or a cat, or what kind of object am I looking at? So whenever you're making a neural network, you have to classify certain things. It's recommended that you would use a softmax activation function as for your output. So I'm actually going to live demo this just so I can show how easy it is to make your own. So I'm going to use VS Code here. I'm going to keep the neural network here on the side. Can everyone see my screen here? I have VS Code here. I have the neural net here. It's a bit small, but I should be able to work with that. I'll just zoom it out temporarily. Beautiful. Okay. So what PyTorch, the name of the PyTorch module we're going to use is everything that involving PyTorch is named in a package, is stored in a package called torch. And specifically, we're going to use what's called the NN module. So I'm going to import torch.nn as NN. So we're getting the NN module. This has a bunch of neural network modules, and we're going to use that. And I'm going to assume that everyone has kind of understands some Python syntax, but if you have any questions, again, feel free to stop me. So we're going to create a new, so every neural network should be stored in its own class. I'm going to call it an ANN. And it's going to inherit from what's called an NN module. So when we first initially create the neural network, so I'm using def init. So when I first create a neural network, this is where you're going to store all of your layers. I'm seeing chat blink a lot, but I can't see it physically. So I don't know if anyone's asking a lot of questions. No, okay, cool. So what you have to do in every neural network module is you first have to say the name of your neural network. This is just a fancy way of saying that this inherits from a neural network module. You need this in every neural network you define. So now let's actually get into the layers we're building. So our input layer is 784. Okay, so we can assume that. We see here that we have one hidden layer that's size 128. These hidden layers are called linear layers in PyTorch. So what we're going to do, we're going to store a new linear layer. I'm going to linear 1. And we're going to say that it is equal to a neural network module linear 1. And what it takes as input is it's not linear 1, it's just linear. Yeah. So since I'm using VS Code and it tells me what I need. So what it tells you here is that it takes number of the size of your input and the output it should give. So let's look at our picture. The input should be 784. So we can just put that in here. And our output should be 128. And we just put that here. And you're done. You've created your first linear layer. Now, we also have a ReLU activation function. So we're going to create a new ReLU activation. It also comes from the NN module. And that's just very simply ReLU. So you don't need to worry about the in-place thing. That's for more advanced concepts. You should just be able to call it here. So great, we've created our first hidden layer. It's a linear layer with input 784, output 128, and it has a ReLU activation function. So let's do that again for the second one. So we're going to create a new linear layer. So for the input here will actually be the output of our first layer, which is 128. And then the output of the second one will be 64. And it also uses ReLU. So we're going to create another ReLU layer. And now we're almost done. So for the very last thing, the output, we're going to say, we're going to have one last linear layer. And our input is the output from the hidden layer 2, so that's 64. And we'll have an output of 10. Now for the activation function, which is a softmax, this is going to use the softmax activation function. So again, that's from the NN module. And this one actually needs an input. In some of the older versions, you won't need to put in input for PyTorch. When the newer versions, they've changed that. When you're coming from after a linear layer, the dimension will always be 1. If you have questions on why that's the case, I can definitely explain it. But if you just want to be able to use it for your own sake, for your own purposes. If you're using it after a linear function, after a linear layer, then the dimension will be 1. I can explain it if need be, but for the time being, I'll just move on. So what we did here is we created our neural network. We created the entire architecture, and it uses based on the picture that we have here. So one last thing that we need in this class is we need to find the forward function. Like so what we did here is we defined a bunch of layers, but how are we actually going to use them? So the forward function will take in our input x. Let's say x is our image. So what we said here. So x is an image of size 28 by 28. So since x is a 28 by 28 image, what we'll first actually need to do is we want to flatten that into a single dimension. PyTorch has a function that lets you do that called view. So what view tells you is it takes in 2 numbers, and I'm just going to write them here and I'll explain what they mean. So what I did here, the -1 tells you that any other parameters that x might have, because although x is an image of size 28 by 28, it might also have like number of channels, the batch size, which is what we're going to use for training. I'll go over that later. So that tells you like the very last part of x should have size 784, and the -1 tells PyTorch deal with everything else automatically. So here we flattened our input into a 784 one-dimensional array, and now we can just start feeding it through the network. So we're gonna first feed it into our first layer. So what I have here is that first it says feed x into the linear layer, then feed the output of that into the ReLU layer. And then we're just gonna do that again. So now for the second layer. So now we're getting the output from our linear 1 to ReLU 1 and feeding into our linear 2 to ReLU 2. And we're going to do it one more time for the last layer, the output one. Okay, so now we fed into our last layer, a linear 3, into a softmax activation function, and we just return the x. And that's it. This is all you need to define an entire neural network in PyTorch. So your init function is where you define your architecture, where you set all your layers. The self dot means that you're storing the layer inside the class, if you're not familiar with Python class syntax. And after you've done that in your init function, all you do is you define your forward function, which takes as input, say x. You can call this input if you want. You should do some pre-processing to the data. So here, since the image is size 28 by 28, I flattened it to size 784, a one-dimensional array, and then I just fed it through all of the layers we defined, and then I returned that. So I will go back to the presentation because I did take a picture of this code. So okay, yeah, this is just a recap of the code that I just produced. Does anyone have any questions of what I just did so far with regard to the code I just wrote? Okay, cool. I'll move on then. Okay, so honestly, after this is, you can pretty much like make any neural network you want with just this architecture, just an artificial neural net. Because of that theorem I gave you called the universal approximation theorem, theoretically, you can learn anything from data with just an artificial neural network, with just linear layers and some activation and like activation functions after. The downside to that is that since artificial neural networks are so general, you don't really know like how many hidden layers you should have, what size they should be, what activation function you should use. And a lot of times people don't really know what they're making when they make neural network architectures. A lot of times just playing around and seeing what happens. So that's why there are multiple types for different types of data. And now we're going to go over convolutional neural networks. And these are very good for image data sets. What they do is they add 2 new types of layers called convolution and pooling. So we only saw one type of layer so far called the linear layer, and now we have 2 more: the convolutional layer and the pooling layer. You can see an image of like kind of how it looks like. It works on some image data, and I'll go over the convolution and pooling layers. So what a convolution is is it applies a filter or a kernel or a convolution. It can be called any one of those three, and it applies it to every pixel in a region in our image. So you can see here, this filter is applied to this region in the image. So it does like 1 times 2, 2 times 4, 3 times 9, so on. And it adds all of that up and places it and kind of sums up all of those features into a single pixel. So you can see why this would work great on images, because what it does, if you apply this filter all over the image, it kind of is able to extract features from the image by kind of like getting a summary of different regions of our image. After that, we have our pooling layer. Pooling layers are typically always used after convolutional layers, and they're usually used to reduce the size of our images. The reason for that being is that CNNs, convolutional neural networks, are quite slow to train. So pooling allows us to reduce the size and also prevents something called overfitting, which is when a model trains too well to our training data set, but it can't generalize to testing data set. So I have an example here. This is what's called a max pool. This is the most commonly used type of pooling. Other types of pooling are average pooling, but max pooling is the simplest and most commonly used pooling layer in neural nets. So what it does here as a 2x2, so it gets every 2x2 region in our image. So let's say we have these 4 pixels, 12, 20, 8, 12. It just gets the max one, and that's 20. Here, 30, 0, 0, 2, it just goes to 30. So yeah, what this has done, it just kind of reduces our image and allows computation to be faster. So we're going to create another neural network, and this time we're going to use a CNN because these are images, and I just said that CNNs are great for image data sets. So the architecture we're going to use is this one. So I'm going to do the same thing I did before. We put this to the side. Yeah. Okay. It's a bit small, so I'll just make this larger. Okay, so hopefully you guys can see this. So this time we're going to make a CNN. I already created the template here. So what we have here is, as always, first we should say super, the name of the neural network, ascribes to NIP. So in every single neural network you make, you always need this. So the first layer we have here is a convolution layer. So what we have here is that our filter or our kernel is 5 by 5. You don't have to worry about the padding. I'm not going to use any padding here. What padding does, that's an optional parameter. It kind of adds pixels to the edges of the image. There are different reasons why you might want to do that, but I'm not going to go into it here. So we're going to create a new convolution layer. So I'm going to call it conv1. Again, all of these layers are right in our NN module from PyTorch. So we're going to say NN conv2D. There's also 1D and 3D versions. If you have like really complicated images, that's like, I'm not sure what a 1D image would look like or a 3D image, but we're going to use convolutional on 2D images. And you can see here that what it takes in is I'll go over to what in channels and out channels mean and a kernel size. Everything else here is optional and I won't go into it, but you can look at the documentation for more information. So the in channels, when you're working with 2D images, this usually refers to whether it's black or white or RGB. Since our images, you can see there that they were black and white, that means there's only one channel because you only need one channel to represent black and white images. They're just one-dimensional arrays from 0 to 255. If any of you took 122, maybe that's a little familiar. So that's just one channel. If our image was RGB, red, green, blue, then that would actually be 3 channels because you need an array of size 3, all from 0 to 255 to represent that. But this is just black and white, so there's just one channel. So what I have here is that this should output to 3 channels. The output channels is also the same as saying the number of filters you want to apply to it. So we're going to say that the number of out channels is 3, or we want to apply 3 filters. And the last thing is our kernel size, which is 5 by 5. And you can do that simply by saying by putting in a tuple, that's 5 by 5. And that's our convolutional layer. The next thing we have, oh, my indenting was wrong. There you go. So the next thing we have is the max pool layer that comes right after the convolution. This is again in our NN module. So this is called max pool 2D. Again, there's 1D and 3D versions, but those would definitely be for different types of data sets. All this takes in here is the kernel size, and everything else is optional. So it says here that our max pooling layer will use a 2x2 kernel. So all we have to do is say 2x2. Okay, so we're going to repeat that again for the second convolutional layer. And I'm actually just going to copy paste these and just edit it. So here we actually have to modify our second convolution layer. The number of in channels will be the same as the number of out channels from our first convolutional layer. So that's going to be 3. And here I put in that we want to output 6 channels. So that'll be 6. And we'll also still be using a 5x5 kernel. For our second max pool, it's going to be the same thing, just another 2x2. And for the very end of our neural network, we're just going to have it go to a linear, or they're also called fully connected layers. We typically do this at the end of a convolutional neural network, so we can make them one-dimensional, and so we can output like something like size 10, for example, because we want 10 classes. So we're going to have one linear layer here, linear 1, and oh, I forgot one thing. I said before that you need an activation function after every layer. So I'm actually going to put that here. This is very important that you make sure you have an activation function. I'm going to use a ReLU layer like we did in the artificial neural network. So what I'm going to say here is we're going to find an activation function for the first convolution layer called ReLU1. And we're going to find another activation layer, another activational layer called ReLU2, and that's just going to be another ReLU activation function. Okay, now let's actually go into the linear layers. So what we're going to do here is, if you remember, we're going to get the linear layer from NN. Now, this is actually tricky because now, before, it was pretty easy to figure out how many N features we want. But it might be a little weird to think about because here we are working with 2D data, whereas the linear layer always works with one-dimensional data. But what you can do is, let's look at our picture. We can see here at the very end, I'm not sure if like it might be too small, but you can see here at the very end, after we've done all this convolution and pooling, we receive 6 channels with 4x4 images. So what that means in total, the number of pixels in its entirety is just 6 times 4 times 4. And if you do the math for that, that's just 96. Or you can also just, since this is Python, you can also just put 4 times 4 times 6. We're going to put that into another linear layer that's also of size 96. So yeah. So that's our first linear layer. So again, if you have questions, you can stop me, but the number of in channels is just the total number of pixels that we had at the very end here. Since there are 6 channels, size 4x4, you just put it in like that. We're going to use another ReLU activation function at the end of this layer. And then for our output layer, we're going to have one last linear layer. So the input here should be the output of our previous layer. So that's 96. And then our outputs, if there are 10 classes, that'll just be 10. And since this is a classification problem, we always need to have a softmax. Okay, and that's it. This is defining the architecture for the CNN. This is a bit more involved than the previous one. But you can see that all we did was just we created our first convolutional layer with max pooling, our second one, and then we have some linear layers that output that has 10 classes at the very end. So let's define the feed forward function that uses all of these. So our input is X. Now, in our ANN, what I did here was I first flattened our 28 by 28 image into a one-dimensional array of size 784. Since our first layer already works with 2D data, we won't actually need to do that. We can actually just feed it right into the the first layer. So what I did here is I fed our input right into the first convolution layer. We didn't have to flatten it or anything because the convolution layer already works on 2D data. So I didn't have to do anything. I just fed it right to conv1, fed it into the max pool, and then did our activation function, the ReLU. So we're just going to do that again on our second layer. So yeah, so this is the second layer, feeding into the second convolutional layer, which kind of does something pretty similar. And now for this, since now we're starting, after we do our second convolutional layer, now we're going to start feeding it into our linear layers. And here, this is where we have to flatten it. So we're going to do the same thing we did last time. So we're going to use the view function to flatten it. The first argument will be -1, telling PyTorch whatever else that x has in the beginning, just do something automatically with that. And then our array, since the linear layer takes as input a 4 by 4 by 6, we're going to say to flatten it to 4 by 4 by 6. This is just 96 if you work this out in your head, but it's Python, so you can make it do the math for you. So once you flattened it, now you can start feeding into your linear layers. So I first fed into the first linear layer, and then now we're going to feed it to our output layer with the softmax activation function. And then now we're going to return x. And that's the entire thing. We've created an entire convolutional neural network. We defined it here in init, and we defined how it would feed forward through the network here. And this ascribes exactly to the picture that I have here. So I'm going to go back to presenting. And I have the code again here. Is there any questions of what I did in this example? Okay, cool. So what I did was define the neural networks, and like that's cool. We can use PyTorch to do exactly that, and it's really easy to do. But how do we actually like use them and train them? This is like the interesting part. Like, okay, we define neural networks, but like, how do I use them? So I'm not going to do live demos of this, so that way you guys can like get to the lab. But what you can do here, PyTorch has another library called Torch Vision. It allows you to do things like loading data or visualize your data. And PyTorch has a bunch of data sets that are natively supported, including MNIST. So you can see here, if you go down here, I'm defining a training set. So that does torchvision.datasets.mnist. The dot after the data sets, you can put in other types of data sets, and you can look at their documentation for that to see what they support. But they do support MNIST. And what you can do, you can specify, I want to store the MNIST data in a folder called data. I'm going to, this is a training set, so training is equal to true. If this was a testing data set, you would say this is false. If you don't already have the data, you can actually specify download equals true. And if you don't already have the data, it'll just download it automatically, which is really cool. And for the transform, it's really important that you have some kind of transform function defined. Honestly, you could probably like copy like something like this for our purposes, which is the digit data set of size 28 by 28. Your transform should at least always have transforms.toTensor. What it tells PyTorch is the image data set could be represented as anything. It'd be like a PNG, a JPEG, whatever. And what the toTensor does is it tells PyTorch, okay, turn this into a PyTorch data set so I can work with it in our neural networks. So you need at least always this in your transform. You can also specify a normalizing function. You don't need this, but it might be helpful when you're training. Normalizing a data set means like all of the images will be shifted to say a normal value so that all images are kind of treated the same. You can check out the torchvision.datasets module for more on how you can load your own data or try out other data sets. The training loop is that to actually use the model that you built, let's say we're using the ANN module that we built. First, you want to we're going to import torch.nn as nn again, the nn module, which is where we got all the layers. You're going to import from Torch the optim module. Optim has a bunch of algorithms to use to optimize your neural network for learning. And then here, the from ANN, import ANN. If I actually go back to my VS Code, you can see I named my file ann.py. So if you're not familiar with Python syntax, that's just saying from the ANN file, import our ANN class. So what we have here is define our network to be the neural network ANN. Our criterion is going to be the loss function. So the NN module has a bunch of different loss functions you can use. For classification, the most commonly used one is called the cross entropy loss. You can look at other loss functions in the NN module. Yeah, if you want to look more into that, they're called loss functions. And our optimizer, which is what we're going to use to optimize our neural network, is called SGD, which is also known as stochastic gradient descent. Every optimization algorithm needs to take in the network parameters. It tells your optimizer you want to train on these parameters of our network. And the learning rate is something that you can actually play around with. A smaller learning rate means that it's going to be more accurate, but it's going to get to the optimal parameters very slowly. Whereas if you have a learning rate that's too fast, it might actually make the neural network train worse over time. So this is something that you can play around with, and it's something you'll get to play around with in the lab. So after you've created your neural network, defined your loss function, your optimization, now you have the training loop. What it says here is that you're going to loop 100 times. They're called epochs. And then for the data in the training set that we created, we're going to grab the inputs like the images and the labels, which would be the classification of the number. So I'm using the MNIST data set as an example again. The inputs would be our images from the MNIST data set, and the labels would be like what they're classified as. So like the image would be an image showing 7 and the label would be 7, for example. So first we grab that from our data. Then we tell the optimizer to zero the gradients. This might seem a little confusing on why you need this, but you always need to call this before in every loop of your optimization for mathematical reasons. When you zero the gradient, it prevents errors when you're training. And now we just feed forward the, oh, actually there's a typo here. It just say feed forward output equals net, and then the net takes as input the inputs. So here, instead of open close parentheses, it should say open parentheses inputs close parentheses. That's mimicking the feed forward function that I showed earlier. So you get outputs by feeding in the inputs into our network. And then once you get the outputs, now you can just back propagate you get the loss by putting into our loss function the outputs, which is what the neural network thinks the digits are, and then you put in the actual labels for the digits here. That will get us our loss. And all you have to do to backpropagate is just call loss.backwards or loss.backward, and it'll automatically backpropagate those errors all throughout the network. And then the last thing you do is just call optimizer.step. I don't want to cover that. The last thing you do is just call optimizer.step, and that tells your optimizer, okay, after we've backpropagated the errors, we want to train. We want the neural network to learn based on the errors. That might have been a bit confusing on how to use the neural networks that we define and how we train it, but you'll see this more in the lab. So is there any question on what I did here? We'll be getting to the lab soon, so hopefully that should hopefully it should answer some questions on what all of this means. If not, then that's it. That's how you train your network, and now you can actually just save the network. PyTorch has a nice save function. So torch.save, we get the state dictionary, and you give it to the file path. So you can call it mynets.pth, and pth is just the extension we usually use to store PyTorch neural networks. So with that said, we can get to the lab. So the link for the lab is located here. I'm going to leave it here for a bit. I there is a big write-up there saying like what you need to do, how you can set up PyTorch on your own machine. I would recommend you use the Andrew machines for using PyTorch, just because I assume in the lab that you're using a Linux environment, and the Andrew machines are a Linux environment. So I recommend you use the Andrew machines. There's some instructions there to set up PyTorch, and you're going to go in and you're going to make your own neural network, and you're going to train on a different data set, not the one I was showing in presentation. You're going to train on what's called the CFAR10 data set. So I'll leave the link here. Is there any questions so far about the entire presentation? Also, if some of you guys looked at the lab now, feel free to ask questions at any point in time. If you're having trouble, we'll be here for at least the next 15 minutes until our next talk. So until then, you can look over it. You can try to set up PyTorch and play around with trying to make your own neural network.